Inverse trig functions are actually something that we've done a lot of. You probably just don't even realise it. Way back, probably year 9 or year 10 would have been the first time you ever saw a trig equation, and you would have been given a little triangle, and you'd have been told some of the sides, and you would have been missing the angle. And the question would have said, find the angle, and you would have gone and used part of SOHCAHTOA, written everything out, and then you would have done this. And if I can get a pen up, there we go. Sine to the minus 1 of root 3 over 2 equals x. And then last year we would have talked about the fact that it isn't just the single solution that your calculator gives you that actually x could be. Obviously within the triangle it is, but on the sine graph there are whole multiples of the value that would work. There are loads, and they go on forever and ever in the positive and the negative directions. This inverse thing, this sine to the minus 1, is literally the inverse of sine. And so what we're doing is we're just going to formalise and explore this concept a little bit more and try and make it a bit of a tighter definition, because at the moment it's a little bit loose, it's a bit flabby. It's kind of, well, you saw it like this in GCSE, and in AS you saw it like this. Let's formalise it. So for us to have inverse functions, we've got to have a few things happening. We have got to have a one-to-one mapping, which means every element in the domain maps to a single unique element in the range. We can't have anything else, otherwise we don't get an inverse, because at some point we would have to make a decision as to where one of our points went. If we have one-to-one, there's absolutely no question, we're just straight off mapping each of those elements in the x to the elements in the y, and there's no questions about it. So what we need to do then is we need to restrict sine, cos and tan down to a domain that just gives us a one-to-one mapping. So you know at the moment sine is a periodic function, so it keeps going. After 360 degrees, or 2 pi, the pattern repeats itself again, and it also does that in the negative direction. I actually want a little bit of that negative. And we want to restrict this function down so that it's got a one-to-one mapping. Now, in the case of sine, if I take between 0 and pi, along this little line here, I've got, well, I haven't got a one-to-one mapping there, have I? I've got two x values, basically, that are going to the same y value. That's not one-to-one, that's many-to-one, and that's going to be an issue for me. So that must not be my range. And the same applies between 0 and minus pi, and so on and so forth. But a one-to-one mapping is found if we go between pi by 2 and minus pi by 2. Now, in between those two values, and in fact including those two values, all of the x values map to a unique y value. And they'll map to a y value in between 1 and minus 1. But there's no other x values that will map to those y values. So we must end up, to create that one-to-one mapping, having to restrict the domain of our sine function to be between pi over 2 and minus pi over 2. So that's our new domain. We've restricted it down. For cos, it's going to look a little different. So cos starts at 1, drops down and goes back up again. Same thing happens in the negative direction. Now if I go between minus pi over 2 and pi over 2 like I did with sine, I've got that many-to-one mapping. I've got multiple x values mapping to the same y value. Look, say there, and also there, they're mapping to the same y value. So I'm going to have to find a different place to cut my domain down by so that I get this one-to-one mapping. Now in this case it's actually a lot more straightforward. It's go between 0 and pi. If we go between 0 and pi, we start at 1 and we capture every y value down to minus 1. So if I restrict x to sit between pi and 0, I'll get that one-to-one mapping there. Let's move all of that up for a minute. There we go. For tan, my function looks like this. I've got an asymptote line at pi by 2 and minus pi by 2. And then the function repeats itself, and this is 180 degree or pi periodic. So it repeats itself every pi rather than 2 pi. And I think you can quite clearly see the one-to-one mapping there between minus pi over 2 and pi. key here is that we don't include pi over 2 and pi, because the function isn't defined on those two values. So we're actually going to go between pi over 2 but not equal to it. Oh, that should be an x. That's annoying. So x is going to run between pi over 2 and minus pi over 2, but it's not going to include those two values. So as we've just thought about then, our sine function, we're going to restrict our domain down to pi over 2 through to minus pi over 2, and we're going to include both of those, and that keeps a range of y between 1 and minus 1 inclusive. So we've got that one-to-one mapping, but we've basically got those values there. For cos, we're going to restrict our domain between pi and 0 inclusive, and that keeps our range still between 1 and minus 1. And for tan, we're going to restrict our domain to pi over 2 and minus pi over 2, but not including those two because the function isn't defined there. And our range is any value in y because we shoot off to infinity. So we'll represent that with y in r, which is obviously the real numbers. So we now know the bits of our functions that produce our inverses, because we've got that one-to-one mapping that we absolutely had to require. But now we need to know what these inverses are and how we would sketch them. So our sine graph looks like this. This is what we've restricted our sine to. It's that bit of sine. Now, inverses we know are reflected on the line y equals x. So that is the kind of diagonal line through the origin, sort of bisecting almost that coordinate axes there. And we reflect our function along that line. So where it would have started, it's very hard to draw these shapes, but you're bending kind of in a sort of a loop around the x-axis, this y equals x line down towards 0. We're going to bend in the opposite direction now. So we create a mirror image, basically. That's what we're looking for. So this terrible line that I've drawn here would represent the inverse of sine. Now, we know this as sine to the power of minus 1 because that's one way of describing it. That's really clunky notation because if you think about sine x, if I want to square all of that, I don't write it like that. I write sine squared x. But sine x to the power of minus 1 is 1 over sine x, and we already know that's something completely different. So it's really, really clunky notation. We've tolerated it up until this point, but now we've got new notation, we're going to use it, because that is really misleading. So this notation we're just going to get rid of, and for some reason I can't rub out anymore, so we're just going to get rid of that. Bye. Bad notation. Bye. This inverse sine we're going to call arc sine. And that's much nicer. That notation is completely unique to the inverse. It doesn't give us anything misleading, and it looks really pretty as well, so that's nice. So just some features of arc sine x then. So it's got this little graph here that looks a little bit more like that. It's sine x reflected over the line y equals x. And we know that for inverses, our domains and our ranges swap over. So we are now on the x-axis ranging between 1 and minus 1. And on the y, we're going between pi over 2 and minus pi over 2 inclusive. For arc cos then, this inverse of cos, well, we restricted cos down to be this part of our function. If I put the line y equals x in and try and reflect it, which is going to take me a while, it's going to start at 1, it's going to bend through and it's going to shoot up like that. So this is 1 now, and we're ranging through to minus 1 in our domain, and we're starting at 0 and running up to pi on our range. So it's the golden line here that's running through. And for arc tan, we are, well, let's sketch out what we've got on tan. Tan, we're going up to but not including pi by 2 because there's an asymptote line there. Let's represent that because we actually shoot off to infinity at that point. reflecting that line on the y equals x line means that I get, well, my asymptote line at pi over 2 and minus pi over 2 are going to become asymptote lines on my y-axis. So I'm going to just construct this over here. So there's pi over 2 and there's minus pi over 2. And I shoot through the origin, so I know that. And as I go along the x-axis currently, I increase up to my asymptote of pi over 2. So now I need to, as I go along my y-axis, increase up my y-axis, shoot along to my asymptote of pi over 2, giving me a line a bit like this, and then completing the pattern, shooting off down like that on the negative y. So just to recap then, our function arcsine x, which is the inverse of sine, you've previously seen it as sine to the power of -1, but we've just talked about how awkward and misleading that notation is, so we're going to use arcsine from this point on. Has a little graph like the one I sketched in the middle there, and its domain is between 1 and -1 inclusive, and its range is pi over 2 and minus pi over 2, because those were the domains and ranges respectively, the other way around, of sine that we restricted it to, so we got that one-to-one function. For arc cos, we chose a different range and domain, well, same range actually, but different domain to restrict that down to a one-to-one mapping. That was between 0 and pi, and so we've got the same thing going on here, and that should obviously be a 0 then there. So when we find the inverse, obviously our domain and our range switch over. So now our domain for arc cos x is between 1 and -1, and our range is between 0 and pi. Arc tan, we had the asymptote lines at pi over 2 and minus pi over 2, but we had that one-to-one mapping in between. So now our range is in between pi over 2 and minus pi over 2, but not including those, because the function isn't defined there. And just where our range for tan was any value in R, now our domain is any value in R. So there is your whistle-stop guide to inverse trig functions.